in the SPCL team led by Professor Thorsten Hoffler. Today I will talk about sPIN, high performance streaming processing in the network. So this is a project started in 2017 and is still ongoing and quite active in our group. So I will make a bit of a recap of this project, where it stands today and what are the things we are looking at. Okay, so if we look at today workloads, let's see if the slides work. Yes, and one sec. Okay, so if we look at today workloads, they range from online streaming services to collaboration tools to large-scale scientific simulations. Those workloads are run on data centers or large HPC systems, and one common thing for these workloads is that they need to exchange an enormous amount of data, and these communications has to happen as quick as possible. Hence, a critical component of this system is the interconnection network, for which it is required to provide low latency and high throughput as, let's say, fundamental requirements. So one technology that today provides that satisfies these requirements is RDMA, Remote Direct Memory Access. Here we have like a sketch of a compute node, and as data is received from the network, basically the RDMA NIC processes this data and gets it directly into the user provided buffer. And this is the nice thing about RDMA. You get the data exactly where you want it to be. It bypasses the operating system. It doesn't introduce additional copies. It's just the data, it just puts the data into the received buffer. However, RDMA stops here. Now, if you want to process this data, you need to get this data up to the CPU register through the whole memory hierarchy, where you can finally access and process it, right? And the question is this architecture ideal for processing data at these high speeds, like we are talking about 400G, for example, today? So, and at that speed, we are getting one packet every 1.2 nanoseconds. And if we look at this architecture with these high latencies, but it's not just a matter of latencies of traversing the PCI and hold the whole memory hierarchy, but also throughput, because then on the CPU, you are sharing, you are competing for resources, you are polluting possibly the caches, and also you can suffer from OS noise. So is this architecture ideal if we can express these tasks, the tasks that process the incoming data incoming from the network on a streaming fashion, right? And the observation is that on this same system, there is already a unit, the RDMA NIC, which is designed to like process data at this speed. So can we extend this architecture in a way such that we can enable user-level applications to express tasks that must be executed directly on the NIC on a per packet basis, so on in a streaming fashion? And this is the basic idea of sPIN. So enable applications to define these per packet tasks. So to better describe, so in this talk, we are going towards three different main topics, like the programming model, then an hardware accelerator that implements this sPIN programming model, and then a set of use cases that motivate the need for programmable NICs, and in particular, application-driven programmable NICs. So to better describe what the sPIN programming model is, we use an abstract machine model. So this is basically the contract that we expose to the programmer that defines then these per packet tasks, and then has to be mapped on different implementations. So in this model, we have a fast shared memory, ideally single cycle latency, then a packet scheduler, so we are getting packets from the network, and then a set of handler processing units. Later, we will see that in the hardware prototype, these are simple RISC-V cores. A DMA engine on the NIC that allows us to move data to communicate basically with host memory through PCIe. And at this point, the CPU, the application running on the CPU, has more of a management role, in the sense that it has to define and install the, let's say, the code, the per packet code that the application wants to execute on the incoming packets. We call these handlers, and to manage the memory on the NIC. We will see some examples later of how this memory is actually used. So as we get packets from the network, those are moved into the fast shared memory and then scheduled on the different HPUs in order where the handlers that the application specified actually run, and that can consume the packet or move the packet to the host memory after, for example, processing it or conserving some state in NIC memory, or moving the data back to the network. So the actual programming interface is based on the concept of packet type. So given a message or a flow, when I say message, you can think of an MPI message or a flow, a TCP flow, for example, or whatever a socket identify, if it's UDP, for example. So, and in this flow or message, we identify three types of packet: header, payload, and completion. So the different packets are processed by different handlers that are specified by the application. So we will have an header handler for the header packet. The set of payload handlers will be processed by the set of payload packets will be processed by the payload handler. And finally, the last packet will have an ad hoc completion handler that can, for example, clean up the state that has been created on the NIC. But to make an example of how SPIN works, actually, let's see how a ping pong performs with RTMA, how a ping pong is executed with RTMA. So here we have multiple packets that are sent from the initiator to the target. So they get to the NIC and then finally to the memory of the target. And then at this point, the application running on the CPU says, oh, I received a ping, then I need to send a pong message. So it's sent, in this case, it's more like of an echo. So it sends back all the packets and they finally get to the initiator, back to the initiator, and the ping pong completes. Now, if we have SPIN, we can actually execute this task of sending back the packet on a per packet basis. So not only we are saving the latency here, but as we naturally enable a per packet processing, we also improve the throughput. So I hope that I gave an overview of the programming model. Now let's see how we can actually implement this programming model in an open source accelerator. So first of all, we need to understand what are the architectural principles for in-network compute. So what do we want from this accelerator in terms of requirements to be satisfied? So one thing is low latency full throughput. This is basically what we said in the beginning. So to achieve that, this accelerator needs to be highly parallel. And the reason for that is that if we plot the time your handler lasts, right? So this is the time you need to process a packet according to your task that you want to execute. As function of the number of cores you need to get to line rate, you see that if your handler lasts for 1 microsecond at 200G, you are going to need about 25 HPUs if you want to keep line rate. You need to double that number if you double also the injection bandwidth. The second thing is fast scheduling. So we also, as we want low latency, so the time as we see from when we see the packet to when we get your handler running has to be minimized. And the last thing is fast explicit memory access, or in general, high instruction per count for the handlers. So as the budget that we have for the handlers, the time budget is limited, we really don't want your handlers spend a lot of time waiting for a load from NIC memory because there is contention or whatever. This is the requirement that we had on like the single cycle latency NIC memory. The second class of requirement is about use cases. So what we are doing here is basically liberating NIC programming. So now it's not about just network function, simple network function like packet steering or RSS that are executed on the NIC, but now it's your application that comes and says, oh, look, I want to execute this task on the NIC. So it really opens up like the scenario to a lot of possible use cases that range from network accelerated non-contiguous data types to distributed file system, consensus protocol, erasure coding, and so on, right? So what we need to support on this accelerator is stateful computation support. So for example, you get one packet belonging to a message or a flow, and then you want to save some state or propagate some state also to other handlers processing different packets belonging to the same message or flow. Think about, I don't know, aggregation. If you are aggregating all the data coming into a message that is split in different packets. You want to share the accumulator, and handler isolation in the sense that you don't want the handlers belonging to application or tenant A to access the NIC memory allocated by the application B or tenant B, right? So the third and last class of of requirements is ease of integration. So what are we basically proposing is to move from this NIC model where we have the network interface, so we get the packets from this side, the inbound engine then moves the packets directly to the host through the host memory, through the host interface, to something that looks like this. So wherein after the inbound engine, there is a SPIN unit that can process packets directly on the NIC, right? So at this point, the inbound engine can take the decision, oh, this packet must be processed on the SPIN unit directly on the NIC, and then the SPIN unit can either send the packet to the host or back to the outbound engine, or the inbound engine can decide to take the classical non-processing data type, data path as it would happen for RTMA. So this means that this accelerator needs to be area and power efficient in order to not dominate area and power of the NIC, and also needs to be configurable in the sense that we want to make it possible to adapt this accelerator to different scenarios. For example, if you are integrating it in a 100G network, 200G network, or also according to the workloads you want to run on those. So we develop pSPIN, a powered implementation of SPIN. So basically, now we extend this pSPIN unit, and here what we have is a set of memories. So these are scratchpad memories. Actually, all the memories presented here are scratchpad memories. There is no cache coherency involved. A packet buffer, a program memory that contains the code of your handlers, and a handler memory that stores the state of your handlers. Right. Then there is an hardware packet scheduler that decides, first of all, on which cluster your packet must be processed. A cluster is like a processing island. Basically, it contains a set of handler processing units, this H here, and those are implemented as a simple RISC-V course, 4-stage pipeline, in order to keep it so as simple as possible. Inside then each cluster, there is a scratchpad memory, which is a single cycle latency, right? While those are slower but bigger, so like these are 20 cycles in order to access this, these other memories. And then a DMA engine that allows us to move data between the scratchpad and the off-cluster memories, and a cluster scheduler that decides then on which specific HPU you want to run your handler. We have other units then, but let's skip them. They are not relevant for this talk. So how does it work? Now, if you have an application and you want to offload something, how do you do this? Well, the first thing to do is define and offload your handlers. So like imagine you have a library of handlers you specified. For example, for telemetry, you will specify the header, payload, and completion handler. Same for filtering or whatever use case you want to deal with. The second thing you have to do is define an execution context. So basically here, you are really modeling like the specific use case. So you are saying, look, I have this filtering execution context with these three handlers, the header, payload, and completion. I have some NIC memory that I pre-allocated, so this will stay here, right? And will be shared by all packets matching this execution context. We'll see this later. And a NOS buffer to act like basically RTMA, in a sense that now the handlers processing your packets can also decide to write to memory as it would be with RTMA, and then you provide a pointer to the buffer sitting in host memory. At this point, once you have the execution context, the last thing you want to do is define a matching rule. So you want to say, for all the packets, for example, for all packets matching this MPI tag, or for all packets that are coming to this socket, I want them to be executed, to be processed according to this execution context, right? And then this matching rule is installed in the inbound engine. At this point, from the network perspective, from the application perspective, you are done, right? So you are ready to get and process packets on the NIC. So from the network perspective, you have now an execution context installed there. And as you get packets, the inbound engine will try to match this packet to a given execution context, right? If it's possible to match it, then it will be sent to the sPIN unit. Otherwise, it will take the classical non-processing data path, right? At this point, if the packet has to be processed on the NIC, the packet scheduler is informed that there is a packet to process and then decides a cluster where the packet must be processed. But also what happens is that the packet is now moved into this packet buffer. But remember that this is a slow memory, right? And we want to access, our handlers are basically very likely, not always, but very likely they are function of our packets, right? So they want to inspect the packet data. So we would like to have them here. And this is exactly what happens in the next step. So this cluster scheduler will then use this DMA engine to move the packet from here to here, and then select, once this copy is complete, it will trigger your handler on a given HPU, right, on a given core. So the scheduling overheads are, because of this copy, are function of the packet size. So for 64-byte packets, it takes 12 nanoseconds from where we see the packet here to where your handler runs. And for 1 kilobyte, that goes up to 26 nanoseconds. So we synthesized the sPIN unit in Global Foundries 22 nanometers, and we're able to close the timing at 1 gigahertz. Overall, in terms of area, this takes about 95 megagate equivalent that can be estimated to be as 18.5 micrometers squared. And the power envelope, and this is the very worst case estimation for us where all cells are toggling, basically, is about 6 watts. So if we look inside if we look to the area breakthrough, we see that here, this is the total area in percentage, and most of the area of this accelerator is taken by memories. These are the 4 clusters that we have in total. I forgot to say this, so we have 8 cores per cluster and 4 clusters in total. So this gets us to 32 cores. And if we look inside each cluster, then again, we have the same situation where most of the data is taken by L1, and this small gray thing here is the 8 RISC-V cores. So if we compare this to a Mellanox Bluefield, for example, the first generation, this will be about 51 micrometers squared in terms of estimated area. So we are about half of that. And we run different benchmarks that allow us to determine that actually the accelerator provides performance in terms of throughput in the target line rate between 200 and 400 G. So if we compare this to like an ARM-based system, so this can be compared, for example, again to a Bluefield, which is ARM-based. So we see that, and also it has a cache coherent memory hierarchy and a fully fledged system, basically. So we see that we are 10x more area efficient in terms of gigabit per second per area. So this is the geometric mean among all these use cases here. And if we compare this, so if we want to run basically the same handlers on this architecture, now on Axion Gold, for example, well, then we are 100x more area efficient. So to move to the last part of this talk, let's try to motivate a bit why do we need this, right? So let's see a bit of use cases where this can be useful. So the first, I will go briefly through 3 use cases. Network accelerated non-contiguous memory transfers, distributed file systems, and finally, we'll see in network already used with sPIN. So you have a non-contiguous memory transfer as soon as you want to transfer data between 2 hosts, and this data is not stored contiguously in the memory of either the sender or the receiver, right? So there are different ways, different languages that allow you to express non-contiguous memory transfer. The one which we think is the most flexible one is actually MPI data types with derived data types that allow you to compose data types and express whatever kind of non-contiguous memory transfer you like. Right, to see how this works in the non-accelerated case, here we have an animation that shows the initiator sending the packets to the target, right? And then the packets go into a temporary buffer because now you are getting the packed buffer. But remember that with data types, now the receiver side is specifying a layout saying, look, I want to receive this data in this particular layout, which is non-contiguous, right? So what has to happen now is that the MPI implementation reads again the data and makes the copy to interprets the data type and puts the data at the right location into the received buffer, right? So can we accelerate this with sPIN? Well, one way is to use specialized handlers. That means given a particular data type that is the representation of a non-contiguous data transfer, then let's write an handler for handling that layout, right, that data type. So for example, the simplest one is the vector, right? So here we have the blue boxes are the ones we want to move, the white boxes are the empty memory that we don't want to transfer. So this can be described by like a set of parameters, like number of blocks, the block size, the type of these blue boxes. This is an integer in this case, and the stride. So like how many boxes you need in order to start the next block, right? So then we write our handler, our sPIN handler, and what we do is basically move both the representation of this data type and the handler to NIC memory. At this point, as we receive data from the network, the sPIN accelerator will trigger your handler. And then we have to do three things. So one is, okay, read a bit from this data structure, understand where exactly, according to the offset in the packet, where exactly we need to copy this incoming data, and then finally issue the DMA writes in order to put the data at the right memory locations. So if we now plot the throughput as function of the block size, so the block size is the number of boxes in each block here. So basically, this is an indication of the complexity of this vector data type. Let's say the smaller is the block size, the more non-contiguous memory regions you have, so the more complex it is to process this data type, right? So this is the host-based unpack. And this is the throughput with specialized sPIN handlers, so doing the unpacking on the fly, basically avoiding this double copy that the host-based version has to do. And we see that as of 64 bytes in terms of packet size, we are actually able to achieve line rate, while the host unpacking doesn't perform too well. However, the problem is that, as we were saying in the beginning, MPI data types allow you to express arbitrarily complex data types, right? So allows you to build these derived data types. And asking you to write a handler for each one of those is not the best thing to do, because they can grow really complex really quickly, right? So the question is, can we define a general handler to process any kind of data type? Well, in this work presented at SC19, we we propose different solutions to these different approaches to this generalized handler. So this is like a library that runs on sPIN on the NIC directly, right? And we end up with this scheme, which is read-write checkpoints, that is able to like match closely the performance of the specialized handler. So now the difference is that you don't have to write that handler for that data type, but is kind of a general handler that you give it a data structure and will process the data type according to that data structure. So we also study different applications or real-world data types used in different applications. So in this plot, we have each tile is basically an application. Then for each application, we have different data types being used by this specific application. And then for each data type, we show the speed up of, for example, in this case of the general handler used in sPIN over the host-based unpack. right? So this red bar is the general handler. This this orange one is the specialized handler, so an handler written ad hoc for that specific data type. And finally, a portals for implementation using IOBEX. So what we see from here is that in different cases like this, we are actually able to achieve up to 10x speed up over the host-based unpack. In some other cases, it just doesn't make sense to offload data type processing, either because the message is too small, so you get really few packets and are not able to exploit parallelism on the NIC for that given message, or the data type is really fragmented. So for example, is a vector of integers with block size 1, and then you need to issue a DMA write for each integer. So this is not ideal for PCIe, for example. In the paper, we have much more analysis. I invite you to check it out. So the second use case I want to quickly go through is distributed file systems. So we know that those are essential to optimize because they can up to 60% of the training time of a deep neural network can be spent in I/O overhead, and this rises up to 90% if we consider large-scale scientific simulations. So if we look at like a storage node of a distributed file system today, it is composed by a set of storage nodes. Inside each storage node, we have a NIC, a memory, a CPU, and then the storage media where the data is actually stored. We have multiple storage nodes. We also have other types of nodes like metadata and management. Those are not important in this context. And then finally, our compute nodes where our application runs, right? So whenever we want to access some data, the first thing we do through this DFS abstraction is to contact the metadata, know where the data is, and then contact directly the storage node in order to access the data, right? So the point was that until now, or until recently, the bottleneck of this system was the storage media. So in this case, it was having little sense to optimize other components like software overheads or network overheads, right? So however, today this is changing. For example, if we consider non-volatile main memories or NVMe JBOF, they actually show performance similar to DRAM, right? So suddenly now it becomes important to optimize software overheads and software and network overheads, right? So one simple solution is to just apply RDMA. RDMA is perfect for this because it just bypasses everything and gets you directly to the storage media. So you just bypass these overheads. However, the problem is that this distributed file system implements some policies like client request validation. How do we make sure that this client is authorized to write some data or to access some data, data replication, or erasure coding? So implementing this with RDMA is tricky and not efficient. So with SPIN now, as we add some compute capabilities directly on the NIC, we can actually re-implement these policies on and make them run on the fly. So a bit like we were doing before on the CPU, but now in a more efficient way. So to make an example here, let's look at data replication. So with RDMA, if we don't want to involve the CPU of the storage nodes, what happens is basically the client has to write to each storage node if it wants to have replicated data, right? So it has to make 3 different writes. Now, if we have SPIN, we can just have some handlers on the NIC of the storage nodes that just do the forwarding of this data. This is replication, is like an MPI, is like a broadcast operation, right? So we can implement this broadcast logic now directly in the SPIN handlers and have them forward the data as it comes from the network. So if we show, if we plot the latency of this write as function of the write size, this is RDMA flat. So is the first example we have seen here. This is the latency if we involve the CPU and implement this broadcast according to different approaches, like a ring-based broadcast or a pipeline binary tree. And then this is the latency with SPIN with the same approaches, so ring or chain-based broadcast and pipeline binary tree. If we use SPIN in order to implement those, so we can get to up to 4x lower latency if we consider a replication factor of 4. Good. So I won't have time to discuss in detail the network or reduce. So basically here the idea is to push the computation deeper in the network. Until now, we were limited to the NIC. And then the question is, what if we now have sPIN directly in the switches so we can program switches freely, right? So or reduce is one of the most important collective operations. So basically we send the data and then we want to get the aggregation back. So these are all the hosts participating to this or reduce. And if we offload this to the network, we can get up to 2x traffic reduction and 2x bandwidth improvement. So in this work, which I won't have time to describe here, unfortunately, we show that there are missing features in today's approach to network or reduce, like they can only support some type of operators and data types, while if you have programmable switches, you can actually use whatever data type. You can support sparse data, and you can also enforce reproducibility. So to conclude, in this talk, oops, sorry. So in this talk, we talked about the programming model that we introduced with sPIN, the implementation of this programming model, the Arthur accelerator, and a set of use cases that we have been looking into. So sPIN is actually open source. You can find it on GitHub, where there is the actual Verilog code, runtime examples. You can just download the container and run your own sPIN handlers. And currently what we are looking in is how to move sPIN in the cloud. So what are the different requirements that these cloud providers, that having NIC programmability in the cloud would require, like QoS, for example, or performance isolation for the different tenants or virtual machines. We are prototyping sPIN by integrating this accelerator into our real open hardware NIC, which is Corundum, and then finally having an FPGA prototype. And we are always looking and implementing and studying different use cases in order to motivate the need of application-driven NIC programmability. So this concludes my talk, and I'm happy to take questions.
Very cool, thank you. Do you have any examples of further use cases you'll be exploring?
Yes, so erasure coding is one of them, for example. So we have seen that there is some previous work where they were exploiting an InfiniBand accelerator or NIC accelerator for erasure coding. And we are doing the same. We are showing how doing this with sPIN on a per packet basis instead of a per message basis can actually be beneficial. And also we are looking at graph algorithms. So how to enable graph, how to accelerate graph algorithms with sPIN. One simple example here is indirection. So if I want to read an adjacency list from a remote node, usually I have to, in a one-sided manner, usually I first have to get the boundaries of this adjacency list. So I get, and then the second step is to actually read the adjacency list. With sPIN now, you can just resolve this indirection directly on the NIC. As you get the vertex ID, you can just then get the adjacency list and save a full round trip.
Cool, thank you very much. Are there any questions people would like to chat in? We are pretty much at the hour, but if anyone like to get a quick question in, we have a few minutes. Okay, well, thank you very much. I enjoyed the presentation very much.
Thank you.